everyone, welcome back to the channel. In today's video we're going to be looking at another example of how to find the inverse Laplace transform of the Heaviside step function. So here is our example. You'll see we've got f of s, that means that you're looking at the Laplace transform, is equal to a function where you've got three terms. Your variable is s, so when you find the inverse, you're going to have an expression where your variable is going to be t. So let's look at the terms that we've got here. The first one you'll see we always start with our denominator, remember. So our first one that we've got, the denominator looks exactly in the same form as number 1 on your table. So that one's fine. If you look at the second term, however, you have an exponent in the numerator and you've got this s squared. So the s squared tells you that you're looking at something, the item number 2 on your table. But this exponent is the problem. And it means that we're looking at the Heaviside step function. And the same thing with your third term. So now we want to put the second and the third term into the same form as your second shifting theorem. So let's just remind ourselves of what the second shifting theorem is. That if you have the Laplace transform of a function that looks like f of t minus a times the step function minus a, that is going to be equal to e to the power as times the transform of f of t. When you're finding the inverse, we remember that we're going to be working from the right-hand side to our left-hand side. So we need to have number 2, your term 2 and term 3 in the same form as this one here. So we want to take out the exponent and leave everything else next to the exponent. That means I'm going to write f of s as 2 over s. I'm going to keep that because there's nothing wrong with that form. Plus 2 times e to the minus s times 1 over s squared minus 2e to the minus 3s times 1 over s cubed. Right? Then I have 2 over s, 2e to the minus s. So we've got, for the second term, we've got the e to the power, as in the second shifting theorem. Now we need to have the Laplace transform, and we need to have the 1 over s squared in there. And in order not to change the value of this term here, we're going to say we want the inverse of that, like that. Because you've got the transform of the inverse, which means they cancel one another out. So all you've done is really change the form of this term so that it fits with the second shifting theorem. Because once you've got that, you can then find the inverse. You can move from your right-hand side to your left-hand side of the second shifting theorem. Let's do the same thing with the second term. So minus 3s, and what do we need? We need the Laplace transform as it is here. And we know we have our function. Let's just shift this up a bit for you. We know we have the function here is going to be 1 over s cubed. So in order to not change the value, you're only changing how it looks. We're going to say it's the inverse of that. So that means we are sitting with 2 over s plus 2e to the minus s. The transform of 1 over s squared is just t. And the transform of 1 over s cubed is going to be 2 times t squared. Right, that should be a half. That should be a half t squared. Okay, so Now that we've got these two terms in the same form as the second shifting theorem, we can now move from our right-hand side to our left-hand side. So that means that we have f of t, because now we can take our inverse. 2 over s, which is going to be equal to 2. The inverse transform of 2 over s is equal to 2, plus 2 times, we know that u is going to be minus 1 because of the shift in your power. The function that you're taking the transform of is t, together with the shift is going to make it t minus 1. Then the second term, you've got 2 times, you can take this, just shift my head out of the way. You can take the half, which is in this expression here. So you can take this half and you can factorize it out. Times a half. Then the inverse of this term, you know you're going to need a Heaviside step function because of the exponent. So there's the shift. The function in front of it is going to be a square function, and inside it is t and the shift. And that is going to be your, and that is what your function is going to look like. The inverse Laplace transform is going to look like in terms of the Heaviside step function. I hope you found that example useful. I will be doing more examples of this because it takes a bit of time to get your mind around what you're doing exactly. So let's go and do some more. I'll see you next time. Bye.